CMInDS seminar. Today, I'm very pleased to introduce one of our own faculty, Amuthan Ramabathan. Sorry, I'm so sorry.
It's okay.
Noting.
It's
Yeah.
Ramabhadran.
Yeah,
Sure. Yeah.
okay, yeah, Ramabhadran. Yes. Yeah. So if it was written in Devanagari, I would have been able to much better able to.
Yeah. So this is actually, in Tamil, what happens is many of these Samyuktaksharas are missing, so the spellings are all very skewed. So it's actually pronounced Ramabhadran. Yeah.
Oh, okay, much better. Yes, Ramabhadran. Yes. He joined us in 2018. He's currently an assistant professor in the Department of Aerospace Engineering at IIT Bombay, and he's an associated faculty in CMInDS. His primary research interests include the development of theoretical and computational tools for multi-scale modeling in the context of crystalline and amorphous materials, wave propagation in solids, and machine learning for scientific computing. He received his PhD in aerospace engineering from IISc and BTech and MTech dual degree in aerospace engineering from IIT Madras. He got his postdoc from Caltech and École Centrale de Nantes in France. Over to you, Amuthan.
Oh, thank you very much, Professor Sunita, for the kind introduction. Should I start or should I wait for some more time?
We can start. It's 5:03.
Yeah. Okay, thank you very much. Yeah, so it's very nice to give a talk here as part of CMInDS. And I'm relatively new to IIT, and I think I don't know many of you who are in the audience here, but I would love to meet all of you at some point in the future, at least once the once everything resumes, the normality resumes. Okay. So before I begin the talk, I think I should perhaps clarify that I'm not an expert in machine learning. I'm more like I use machine learning and to inform my own research. It's been a lot of fun. I'm learning a lot of things as I go along, and I'm sure that there's a lot more to learn. I should especially thank my wonderful colleague, Prabhu Ramachandran. I presume he's also here. So the work I'm going to present today is work done jointly with Prabhu. And it's been wonderful collaborating with Prabhu. And it's fair to say that the work really got a lot of momentum because Prabhu's has been around. So this is work that we just started this year. Actually, we started working on this, from scratch in some sense, but this January, and so we are still learning a lot as we are every day about these ideas. So what I want to share today is some recent work that we have been doing that we published in this area, and also talk a little bit about where we are heading next. Okay. Yeah, so talks in the recent weeks where people talked about interpretability in the context of machine learning, but the sense in which I use the word interpretability is slightly different, and I'll spend some time clarifying that. But the larger focus of this talk is to present a class of sparse neural networks which are interpretable. Okay? And in the process also highlights some connections between traditional numerical scientific computing models and modern machine learning algorithms. That's the larger goal of this particular talk. Yeah, so the outline is as follows. So I'll first introduce a couple of traditional numerical methods in scientific computing, just to highlight what exactly I mean by interpretability, because this term obviously means very different things to very different people. And then I'll talk about the most popular approach in the application of ML to solve partial differential equations, and then present our solution, which we call SPINN, and which is a class of interpretable neural network models which seem to perform well. And finally, I'll very briefly discuss about the larger question of whether we can interpret general ML models. Now, I don't have the answer to this question. Okay? I don't know if it's possible to interpret full general ML models, but at least I want to share some insights that have come up from our work. Okay. So differential equations are quite natural when you study physical systems, right? So especially when you have, when you prod a system with some kind of input and you want to understand how the system responds, oftentimes this takes the form of a differential equation. Okay, so if you have an infinitesimally small change in your input, how does the output of the system can also change infinitesimally, but the changes can be related to each other. And the precise way to encode such changes is by a differential equation. For instance, here is an example of an aircraft wing. So I won't be talking about real applications today, but just to set the motivation. So suppose you know the loads that are acting on this particular wing, and you want to understand what is the deflection of this particular wing. Then, if you work out the mathematics here, it turns out that it's governed by a partial differential equation. So the displacement of the wing at any point on its domain is governed by a partial differential equation. In this case, you have an elliptic second order partial differential equation, and you often have to supplement them with boundary conditions so that you have unique solutions. Okay. Now, this is the point here is that differential equations are quite natural. They arise very naturally in scientific applications. Now, I won't be focusing on any one particular application, but rather I'll focus on differential equations in general and talk about how machine learning has been used and in this context and how our work comes into this particular setup. I'll very quickly, so this area is fairly mature, right? So for instance, if you look at the solution of differential equations, these have to typically be done numerically because we don't have closed form analytical solutions typically for most differential equations. And there are many interesting and fairly mature numerical techniques to solve differential equations, like finite differences, finite elements, meshless methods, and so it's a huge zoo of methods. I'll very briefly talk about finite elements and meshless methods using this simple equation that you see here as an example. For two reasons. One is that it will help me very clearly articulate what I mean by interpretability. And two, it's also going to inform the development of our the method I'll be proposing later on. So here is a simple ordinary differential equation. So you have an unknown function u defined on an interval AB, and it satisfies a particular equation. The negative of the second derivative is equal to a prescribed function f. So typically, if you are, let's say, given a function which is continuous on this particular domain, you want to find a twice differentiable function that is able to satisfy this equation, of course, which also satisfies the appropriate boundary conditions. Now, this is what I would call as the strong form of the differential equation. This is for reasons that will become clear very soon. A very standard way to solve this is what is called as the finite element method. And a finite element is basically a very smart subspace projection algorithm. So what you do is you weight your differential equation with a test function belonging to some appropriate function space. So in this case, it turns out that if you look at the this particular Sobolev space, this space of functions which are square integrable, whose derivatives are also square integrable and which vanish from the boundaries, that's an appropriate function class to test these differential equations. And this also relaxes the requirements. So instead of requiring the function f to be continuous, you can in general have a less stringent requirement like L2. It can belong to L2 first. So what you do is you recast the differential equation in a weaker form. So you see that on the left you have a bilinear form, and on the right you have a linear form. And v is an arbitrary function belonging to this test function space, and u is the solution that we seek. So we want to find a solution u that satisfies this equation for all v. And for that reason, it's also called as a variational statement of the differential equation, or the weak form of the differential equation. Now, the key idea in finite elements is that instead of solving this weak form in the original function space, you solve it in a finite dimensional subspace. Okay, and the entire strength of finite elements is the fact that you can do this very efficiently. Okay? So technically, what you do is essentially a projection. Okay? You're projecting the true solution onto a finite dimensional subspace. But the beauty of the finite element method is that this projection is optimal with respect to a particular norm. So the norm that is arising from this inner product, it's called the energy norm. So it's optimal with respect to that energy norm. So these are fairly well-established numerical methods. And the finite elements especially has a very, very rich mathematical theory, which goes back to decades. And by now, it's a fairly mature technology. So just to give you an example of how this projection works, suppose that you have the simple one-dimensional differential equation. The first step is, of course, to discretize the domain into using a mesh. Okay, so here in one dimension, it's a simple partition of the interval AB into a set of disjoint intervals. And once you have this partition, this mesh, you define very simple functions that have compact support on this mesh. So here is a piecewise linear function, which has a support only in around the vicinity of a single mesh point. Okay. And the finite dimensional subspace on which finite elements projects the solution is essentially the linear span of all these hat functions. Okay, that's the basic idea. And once you have this particular setup, you work out that the math and the complicated partial differential equation reduces to a beautiful algebraic equation. So the finite element subspace projection essentially amounts to solving this simple algebraic equation. Okay, so and that's one of the reasons why it's extremely fast. And what is also nice about the finite element method is there's a natural way in which you can refine the solution. For instance, you can make the partition a finite partition that's going to give you a better solution, and the rate at which the error decreases is very well understood. So you have very good bounds on the error behavior, very good control on the error behavior. Good. Another class of methods which are used are what are called as meshless methods. So I'll very briefly talk about one particular method, which is called the radial basis function based approximation. A radial basis function is very simply a smooth function, right? And so it does not have the compact support property that finite element shape basis functions have, but these are in general they can extend over the entire domain because they're not in general compactly supported. But and also there is no definitive mesh, unlike the finite elements. So what you have are a cloud of points, and on each point you have these basis functions sitting on those points. Okay? So the radial basis function approximation essentially amounts to a span of these shifted and scaled versions of the basic mother kernel. So if phi is your RBF kernel, I just use the word kernel to describe this function, then you shift and scale the same kernel across multiple points in the domain, and you linearly combine them, and that gives you an approximation. Okay, and typically the way you would solve an find these coefficients is by using some form of a collocation method. For instance, say you define what is called as a residue of the strong form of the differential equation. So if you recall our equation, it's this is our equation u double dash plus f equals 0. Now this quantity goes to 0 if u is the exact solution, but if it's not, then it in general is non-zero. And the deviation from 0 can be used as a measure of how good or bad the solution is, and that's the residue. So what the collocation methods do is they enforce the residue to be 0 at certain select points. Okay, and that allows you to compute the unknown coefficients of the model, the parameters of the model. Or if you have more points, you can also have a least squares formalism of the same method, etc. There are many variants. But the point that I really want to emphasize, and the reason why I brought these two up, is because both finite elements and meshless methods are interpretable in a very specific sense. Okay? So let's take the finite element solution, for instance. It tells you that the solution is a linear combination of certain basis functions, but the coefficients are, once you solve them, this is an optimization problem, right? So the way I've set it up. And once you solve this optimization problem and learn what these parameters are, they are, you know exactly what those parameters mean. In this case, if I look at the point, the mesh point xi, and the value of the function is ui, the value pretty much tells me that that is the function value at that point. And this is nice because let's say that I look at this region of the solution and I see that there is a disagreement between what I see as the actual function and what I see as the approximated function. Then you can naturally, conclude that maybe if I refine the mesh around this region, that can give me a better solution. So understanding how what these parameters mean has a huge impact on how we develop better approximations. And the same holds true for an RBF approximation. So here, all these parameters of the model U, X, H are all interpretable. So you know exactly what they mean, and if you have a solution which is not performing well, you know where to look at and where to focus to to make it better. Now, this is in contrast with what happens with typical neural network applications, right? So if, for instance, you go back to the simple problem that I mentioned earlier, suppose you have some physical system and you want to query the solution at a particular point. What people typically do is they represent this field U as a neural network. So for every point X, you have a U associated with it. And that dependency is captured by some neural network, which is essentially saying that you're going to model it by this kind of a nonlinear function. So you have a bunch of parameters, W, which consists of these weight matrices and the bias vectors. And it's essentially a composition of these linear and nonlinear functions next to back to back, right? So that's a simple way to look at it's the parameterized model. But the problem is, say suppose that you learn a particular, by some process you learn what the solution is. There is no direct way to connect these coefficients, these trained parameters, with the solution. So in particular, if I say that I get a solution, I expect it to perform in a particular way in a certain region of the domain, I see that it is not performing well, and you want to understand how you can refine it. There is no obvious way in which you can say, okay, look at this parameter or look at these parameters, etc. Again, there is no natural choice of architecture. Should I use a 5-layer network or 100-layer network? There is typically, it's typically ad hoc. Right? So people tend to do this by trial and error. And this is one of the problems that I want to address in this document. So can we do better than this? Right? So that's the goal. Now, having said that, I'll very briefly talk about this whole area of physics-based learning, since there are it's slightly different from supervised learning. So let's say that you want to let's focus on the simple case of function approximations. Okay? If you look at it from a supervised learning context, what you're essentially doing is you're looking at a finite subset of the graph of the function, and you're solving this optimization problem where let's say you minimize some loss. In this case, it's the squared L2 norm, and you minimize it over a parameterized function class, say, set of neural networks, and then there's a standard theory that's associated with it, right? Now, in physics-based learning, what happens is you typically don't use an L2 loss. And the reason is that when you do an L2 loss, what you're essentially saying is, I don't care about what is happening in the physical system, but I'm just going to look at it as a vector in some high dimensional space and try to find its distance from L2 distance from some other target value. The problem, of course, is that you're imposing an L2 structure or a vector space structure in the first place to these values, and then you're imposing a particular norm, which need not actually be even existent for the general problem or even relevant, even if it exists. So in physics-based learning, what is typically done is you use some physically relevant loss. So if you are solving a physical system, oftentimes most theories in physics are variational in nature. Okay, which means that there is a variational principle, variational principles are essentially infinite dimensional optimization, right? So that's there is often this variational principle which guides the formulation of physical theories, and many of the physical theories can be viewed at the governing equations can be looked at as the optima of these variation principles, the minimizers or maximizers of these variation principles. Right? So why not directly use that as the loss? That's the basic idea in the larger field of physics-based learning. So here is a simple example, for instance. So you have a variational principle where if you have, let's say, a functional that depends on not only the function, but also the gradient of the function. Here is a concrete example. So you have a specific function which depends on the square gradient of the function, etc. Now, solutions in traditional calculus of variations, the optimizing this will give you a different partial differential equation. Okay, that's a well-known theory. So you can use that as a loss, for instance. Or you could also use the strong form. For for the specific example I showed earlier, if you look at this particular functional and you work out the math, it turns out that the corresponding Euler-Lagrange equations are these elliptic partial differential equations. Okay? And so you can use the strong form, the residue of the strong form of the equations themselves as a loss, and bring in the boundary conditions using some kind of a penalty term. Okay, so these also can be used as a loss function instead of a typical L2 norm. So these are typically how the loss is not something that is a simple L2 loss, but it's often more involved. And in general, physics-based learning uses information about derivatives also. Okay, and this is important to understand because if you, even in a very simple setting, right, if you're looking at function approximation, two functions which are close in the L2 norm can be quite far away with respect to the H1 norm, for instance. So it's important to and typically these derivative information is very important in physics-based learning. So here is a simple example that I have adapted from this hypertext book. So suppose that you have data which is like this yellow or whatever color that is points, and you feed this to a supervised learning algorithm. Obviously, it's going to pick out the mean of these, which is just a straight line. Okay, the zero, so it doesn't get it. But if you run the same algorithm on a physics-based learning using physics-based learning, it picks up at random one of these branches with the probability of 1/2. It either picks up the top branch or the bottom branch. Okay, so even though there are structural similarities between supervised learning and physics-based learning, they do not often produce the same results. And another way to look at it is that in a traditional supervised learning, you have features and labels. You don't have that here. You just have features because and that goes into minimizing a particular loss. And typically, if you have a differential equation, you don't know what the target values are. So there's no target value. That's directly encoded in the loss. Now, when coming back to the context of differential equations, which is where we wanted to focus on, a very common and a very popular idea in physics-based learning is to use the strong form of the differential equation, and in particular use the residue as the loss, the squared residue as the loss. And again, the boundary conditions are brought in by evaluating it on the boundary as used in a penalty kind of formalism. And of course, the residue is in general a continuous function. Let's say it's defined in an integral sense, but you discretize it by evaluating at a finite number of points in the domain, which are what are called the sampling points. Okay? Now, so this structurally has, it looks like the sum of individual terms, which is similar to what you have in supervised learning. And this loss is, this is the physics-based loss that is the most popular variant in the, when solving differential equations with neural networks. So all you do is you parameterize your unknown solution field U as a neural network with some trainable parameters, and then you minimize this loss, and that tells you what the that helps you find the solution to the differential equation. This idea is actually quite old. It was proposed in 1998, and I think it says something that this is the state of the art in 2021. Okay, I mean, not this itself, but the same idea, but cloaked under the guise of automatic differentiation and modern packages like TensorFlow, essentially goes by the name of PINN. Okay, it's a very old idea, but it's marketed differently, and it's called physics-informed neural networks. And so it was published in 2018, and now it's everyone is crazy about it, and I'm still trying to figure out why, but it is what it is. And this is a very popular thing, judging just by the amount of attention it gets. So, but there are too many variants of this to list now. So there are every day you have papers, exploring some variation of this. You tweak this, you tweak that, you get a new formalism, etc., etc. So it's very hard to keep up with these variants. But there are some unfortunate common denominators to many of these models, and some of which I mentioned. So the choice of architecture is quite ad hoc. So let's say that you have some differential equation and you solve this using a neural network. Why do you choose that particular architecture? Why do you want to choose an architecture with, say, 5 hidden layers and 200 neurons each, or 100 hidden layers, 5 neurons, whatever. Why do you choose that architecture? And they're grossly inefficient compared to traditional methods. So if you were to run the same solve the same differential equation using finite elements and using any of these physics-based leveling algorithms, FEM is typically orders of magnitude faster. It's not even in the ballpark. Okay, so that's let's just get it out there first. And to top it all, it's deep learning methods are not interpretable, right? So because interpretable in the specific sense, I told you that if you have a bunch of weights and biases, which we say is the trained model has these weights and biases, then there is no obvious way in which you can connect them to the final solution, apart from saying that a particular combination of them, a particular nonlinear combination of them, is what gives rise to the solution. Okay? So that is so these are all some problems that I want to talk about. Okay, and given the state of affairs, actually, to be very honest, there is not a lot of incentive to use deep neural networks to solve differential equations in lower dimensions, especially. Okay, but what we are trying to do here is to say that maybe if you can, instead of using full deep neural networks. Yeah, sorry, was there a question? Okay, so okay, so what we're trying to say here is that if you sparsify the architecture, you can do so in a manner that is more efficient than deep neural networks, but also is interpretable. So that's the story that we are trying to approach here. Okay? I think someone's mic is on, so if you have a question.
Yeah. So Diksha, I don't know. I see Diksha's mic might be on. I don't know. So if either we can ask the question or please mute.
Yeah. Okay. Okay. So I think I'll go ahead. Thank you. So the starting point of our work was this beautiful paper by He et al., which essentially says that if you look at a finite element model with piecewise linear finite elements, that can be exactly recast as a ReLU deep neural network. It's a beautiful paper, actually. And it's very easy to see that in one dimension. So if you look at the hat function here, which I introduced as a shape basis function earlier, that can be written exactly as a combination of ReLU functions. And this is very straightforward to verify. It's a simple substitution that shows you that this is true. And if you put this together, a finite element solution in 1D is just a linear combination of these basis functions. So you can write this as a particular kind of a ReLU deep neural network. Now, this is fantastic because the biases of this particular network tell you what the nodal positions are, and the weights of the network immediately can be, from the weights of the network, you can extract out what the function values are, which means that this network is great. If you train this network and you get a trained set of weights, you can immediately interpret them as a known finite element solution. This is fantastic. Okay. Now the problem, of course, is that this construction, this explicit construction, works great in one dimensions, but in higher dimensions you only have an existence proof. You don't have a constructive proof. I mean, that's still a good thing because it tells you that any finite element approximation can be recast as a ReLU deep neural network. In fact, there are more general results. If you take any ReLU deep neural network, that is equivalent to a continuous piecewise linear function, except that the region over which each linear function operates is not in general a simple polytope. It can be a different polytope. So for instance, in 2 dimensions, it need not just be a triangle. It could be a triangle, a square, or an polygon, etc. Right? But in finite elements, all the elements have the same shape. Okay, so in some sense, finite elements are special kinds of deep ReLU networks, piecewise linear finite elements. And so this paper was our starting point, which was that it is possible to construct special architectures which can be interpreted in a traditional sense. Okay? But the problem is, if you try to, you can construct the equivalent of single shape functions in higher dimensions using the same idea, but putting them all together as the finite element ansatz is not that simple. It's kind of tedious. So what we decided to do was to instead go for meshless methods, because in meshless methods you don't have this additional constraint of having to construct a background mesh. You just need a cloud of points. Now, once you have, then the idea is kind of pretty obvious, right? So the idea is that you first recast the input. You broadcast it across several points scattered in the domain, shifted in scale forms like this. So suppose that you have nodes at locations x1, x2, all the way up to xn. Then the norm of x minus xi divided by hi, that it in some sense is a scaled version of this, shifted and scaled version of the input. Okay? And you subsequently operate that upon a kernel, and that gives you exactly an approximation like a traditional meshless approximation. Okay, this is in fact an RBF approximation. But you can do more actually. You can go beyond that. For instance, if you want to extend the ReLU activation functions, and of course you first have to smoothen it out, because if you have a simple ReLU, it's not differentiable, it's not quite differentiable. And as I mentioned, higher derivatives are important in physics-based losses. You need to have a differentiable function. So if you use a soft plus activation function, for instance, as a smoother version of ReLU, you can actually use these kind of combinations, which are special sparse networks, which give you something that looks like a kernel in a meshless method. Now, once you have these kinds of, this is not an RBF, by the way, this is not a radial basis function, but it is structurally similar to that. Now, once you have these kind of functions, you can compose them in any way you want. For instance, you can have this initial mesh encoding layer where you can precisely interpret the nodes as the biases in terms of the coordinates of the points, the weights as the appropriate widths associated with the points, so a radius of influence, if you will, associated with each point. You can generalize the kernel to be an arbitrary neural network. Okay, and then finally you linearly combine them, and the final layers values, the weights, they actually tell you something about the specific linear combination of these basis functions, which give you the side solution. You can also port a lot of ideas from standard meshless methods, like if you have a partition of unity method, which is what I've shown here, you can translate them entirely into the neural network language. So this way of looking at things actually kind of provides a nice bridge between two very different ways of thinking about numerical solutions. On the one hand, you have complete black boxes like deep neural networks or interpretable traditional models. But these kind of networks, which are not fully general, okay, these are sparse and these are not, these are not the same as fully dense deep neural networks, but they're somewhere in between. But the nice thing is that you can interpret the weights and biases. So in particular, if I give you a particular if you train such a network and you get the biases and the weights, then you can actually visualize them and relate them to the actual solution. I'll illustrate that now with a few examples. Okay. Now, to start with, let's just take a simple one-dimensional example, a simple ordinary differential equation. There's nothing fancy about this. It's a simple second-order differential equation. Now, of course, you do the train the model and it gets the right solution. That's not the interesting part. The interesting part is what happens. How can we post-process the solution? So in this one-dimensional example, this is a problem with 3 kernel points. Okay, so once you train the model, the parameters of the model immediately tell you where the kernel points are situated, where the nodes are situated. And in this case, you can see that they are actually centered around the region where the gradients are very high. So if you look at the solution, something interesting is happening in this region, but nothing interesting is happening here. So you really don't need to place a node here or here, you only need something here. And the trained model is able to automatically place. We initially had a uniform distribution of points placed or we also tried random points, and they eventually cluster together into the regions of interest. So this is nice because once you train your neural network, these kind of sparse models, which we call a SPINN, these SPINN models are able to, you can extract out the relevant local information. You can precisely say that these are linear combinations of these specific nonlinear functions located at these points. And these functions have a certain width, which is encoded by the H parameters, right? So and this is all straightforward. It comes directly from the trained model. You don't have to do any extensive pre-processing. The parameters are themselves interpretable. So, they are actually more efficient. If you look at the same problem and you look at the performance of our method, I should tell that we call it a SPINN. It's a spin on the word pin, and just, I think, got a little coffee with the name. SPINN stands for sparse physics-based and interpretable neural networks. So, if you look at these kind of sparse architectures, they actually perform much better. They're faster than deep neural networks, and they actually get the right kind of accuracy. And these are not restricted to one-dimensional problems. You can also extend it to higher dimensions, arbitrary domain shapes. There is literally no restriction on the shape of the domain or the linearity, non-linearity of the differential equation. They are quite robust in terms of their application. So I'll just show a couple of examples to illustrate that. So this is an example of a Poisson equation in 2 dimensions. So it's a simple partial differential equation, the Laplacian of a function +1 = 0. And I'm solving it on the square domain minus this line. Okay, it's a square slit problem. And what I'm showing here is a solution that is computed by the SPINN model. And it also agrees with benchmark solutions computed with finite resolution. Once we get the trained model, here is how we are able to visualize the weights and biases. So you see that what you're training is actually a sparse neural network, but you're able to visualize what is happening. You're able to visualize the weights and biases of the network precisely as nodes located at various points having a particular zone of influence. And these are not post-processed, as I said, they are directly coming out of the solution. So if you have a network which has the biases of the mesh encoding layer or directly give you the position of the nodes, and the weights of those mesh encoding layers tell you what the radii of the zone of influence are. And if you look at the weights of the final output layer, that tell you what is the relative weight of each of these points. Okay, so you can see that we initially place these points uniformly on a square grid, but they quickly move around to adjust themselves according to the solution profile. And more importantly, the sizes of these zones of influence also adapt themselves according to the problem. So near the square slit, where you require a finer control over the handling of the boundary condition, you see that the radii of these zones of influence are much smaller, whereas in the interior of the domain, where you really don't have such constraints, the radii are much larger, and they also kind of align with the gradients. Now, we have tested this across different kinds of partial differential equations. So here is an example of a time-dependent problem, which is a parabolic partial differential equation, which is the one-dimensional heat equation. So there are multiple ways to solve it, right? So here you can think of this particular problem as on the left-hand side, you have a time derivative of a particular field. On the right-hand side, you have the second spatial derivative of the same field. And so you can treat space and time as 2 independent coordinates and in the same footing. Okay? You don't need to treat space and time separately. That's what we call as a space-time solution. So it's basically a 2-dimensional problem where 1 dimension is space and 1 dimension is time. Or you could combine them in interesting ways. Right? For instance, you can do a time stepping where you step forward in time on the left-hand side using a traditional method like a finite difference method, and you use a neural network method like SPINN on the spatial part, and you can come up with all kinds of interesting combinations. So here is an example of an implicit scheme that tells you how the solution at each time step is computed using a SPINN, and then this is iteratively taken forward. Okay? So this update, by the way, is not a gradient descent update. It's the time step real-time update. At each time step, you have a gradient descent running to compute the actual solution. That's how we look at it. And we get fantastic solutions, irrespective of whether you use the space-time version or the finite difference, hybrid finite difference version. It tracks the solution pretty well. So here, for instance, you have the space-time solution. So you initially have a profile that looks like that. And over time, it's a diffusive equation. So it kind of flattens out. And so it's a heat equation. So it has a diffusive character. And that's exactly what the space-time solution says. And what you're seeing on the top left is basically a time snapshot of these solutions at various time instants. And we're able to very clearly see how the solution adapts over time, whether you use the space-time or the finite difference variance. And in each case, you can actually query the solution as before and find out what exactly the nodes are doing, what exactly are the weights and biases doing. In this particular case, you can precisely begin to ask questions like here the solution is bad, so maybe I should add more nodes here to refine the solution locally, etc. This is something you cannot do with a traditional deep neural network. You have no idea which node to query, which node not to. How do you change architecture? Those are all still open questions. Now, I think I have an animation here, perhaps. Okay, anyway, never mind. Okay. So here's an example of a hyperbolic partial differential equation. So these are solutions which admit a traveling wave kind of a profile. So the time derivative and space derivative have the same order here. So if you have an initial profile that's bell-shaped here, that just translates in time as the solution that this translates in time. Now, if you look at it in a space-time perspective, so you have an initial profile that looks like that at the back, and then you see that the wave is represented by this kind of a slanted profile. This is naturally coming from solution of the differential equation, and of course our methods capture it completely fine, irrespective of whether you use either of these schemes. And this is my favorite figure from the entire paper, which is that we place the nodes initially uniformly distributed, and once you learn the solution, the nodes beautifully align themselves along the wavefront. Okay, this is something that so in some sense it knows what the solution is. It learns the solution properly, and you're able to tell that it learns the solution because you can query the weights and biases of the network, and you see that they beautifully align along the wavefront. And you also see that on the wavefront they have relatively smaller widths, zones of influence, because you need a tighter control. Whereas in regions where nothing is happening, where the solution is flat, you have this really large. Sorry, first open an animation. Okay, never mind. So on the regions where you have nothing significant is happening, you see that there are these larger zones of influence, right? So this is nice because you can really see what the network is doing and what kind of local minima is it learning. And let me quickly see if I can open the animation differently. Okay, good. So here is an animation of the same picture, so of the same training process. So initially you have nodes which are uniformly placed. So I'm just going to run the simulation forward. This is a real-time simulation, which means that at each time instant, a gradient descent algorithm is solved, and then I'm plotting the final solutions. Okay? So if you look at this solution, you see that the nodes are automatically aligning along the wavefront, even though we did not give any information about where they should be. This is nice for multiple reasons. First, of course, you see this multi-resolution capability, which is inherent in the problem. So you see that the network learns the solution all right, but the solution is physically meaningful. It adapts itself. The widths are adapting to the traveling wave. And also, this tells you that you can do smart initializations to speed up the convergence. For instance, in this case, you expect that there is a traveling wave. So if you initialize the nodes along the physically relevant regions, okay, you expect the convergence to be faster. Okay, so this gives you a lot of handle on how to choose the network architecture. For instance, in this case, I know that I need a lot of points on the wavefront and relatively lesser points outside it. So I can do a quick back of the envelope calculation to figure out how many nodes I need. And that tells me what the network architecture is. Right? So there are rational ways to choose the network architecture. So these are these are the advantages of having an interpretable, at least some kind of interpretability in our model. So let's go back to the presentation. We have also tried this with nonlinear equations, which are a little more severe at times. For instance, here is an Implicit-Burger's equation. So these are equations where the solution develops a shock or a discontinuity. So for instance, what I'm showing here is the initial profile, which is like the inverted parabolic hat. And over time, this parabolic hat kind of skews to the right, and at some point it becomes sharp. Okay, so there's a discontinuity, and this is also called as a shock front. And so these kind of solutions are quite tricky to capture in general, but we are able to get reasonably good solutions. For instance, the finite difference version performs especially well. The hybrid finite difference and SPINN version, it's able to track the solution and also the shock front. The space-time version performs relatively, it's not as good in performing that, but again, this is something which is a discretization issue. We're still working on that. But you have the same kind of advantage now. So you can, once you're given an initial random position of, random initialization of the network, over time, you can see that the nodes align themselves along the shock front. And you can also see that the widths of the nodes are really, really small on the shock front. That's exactly because there's a very sharp gradient there. So you need really, sharply concentrated functions to capture those variations, and that's exactly what you see here. Okay? I think there's also an animation here. Yeah, so this is a slightly different initial condition, but what I'm going to show is what you can see is how the profile develops over time. So in this case, I'm expecting a shock at the location 0.5 x equals 0.5. So let's see how that works. So initially, the profile looks like a sine wave, and then over time, this network learns the solution. The nice thing about SPINN is that you can track how the network learns it. Okay, so you can clearly see that the nodes are clustering towards the shock front, where they have very small widths, and they're able to capture this singularity pretty well. And we have validated these results with traditional numerical methods to make sure that the solution that we obtain are indeed correct. Good. We have also done some work on some semi-realistic problems. Okay, so this is an example from fluid dynamics. It's a standard benchmark example called a lid-driven cavity, and the idea is to solve what is called as the incompressible Navier-Stokes equations. This describes a steady-state motion of a fluid which is enclosed in a two-dimensional domain as 0, 1, 0, 1, and you solve for the horizontal component of velocity u, the vertical component of velocity v, and the pressure p. Okay, subject of course appropriate boundary conditions, and we have been able to validate the results. This is the solution that we get from our network, and we have been able to validate those results both with traditional meshless methods like smooth particle hydrodynamics. So this is a subject on which Prabhu is an expert, and he has this open source package called PySPH, which does an amazing job. And the interesting thing is that we are able to get comparable accuracy with traditional solvers with much fewer points. And that's actually quite encouraging, because it tells you that the adaptive capabilities of this network are indeed, there is something interesting about it. So I don't think we have fully explored all the all possible cases, because we're still in a we started this work recently, so we are still working on finer applications. Good. So I'll stop the list of applications and very briefly talk about certain other features of the modeling. First is that it's directly, it's kind of straightforward to experiment with other variations of this kind of, this way of looking at neural networks, okay? As, for instance, you can directly encode physical problems with variational principles, as I mentioned earlier, in the same formalism. You can also do some cute things like, if you have a Fourier network, a Fourier series, that can be encoded precisely as a network with a special scaling layer and a activation layer and so on. And you can generalize this also. You can. There are lots of these variations that you can play around with, and we have given some examples of this in our paper. But the bottom line, really, I'll summarize because I think we're also running out of time, is that we have proposing a new class of architectures called SPINN, which generalizes radial basis function networks, RBF networks. They are still in the same category as physics-based learning, in the sense that they use physics-based loss functions, but crucially they avoid mesh generation, which can be a pretty costly process, especially in 3 dimensions. Right? So, and our method is constructive, which means that you have a pretty good handle on how to choose the network architecture. It's not arbitrary like deep neural networks, where you choose the network architecture by trial and error, right? But here we have a rationale, because if you know something about if you have some intuition about what the solution should be, you can place the nodes accordingly, and that gives you a simple way to estimate how many nodes you need, and what the architecture of the network has to be. Okay? And precisely because of the fact that it's not a dense network, it's kind of sparse by construction, it's quite efficient in comparison to deep neural networks. And crucially, these networks are interpretable. It's interpretable in the same sense as traditional models. And I should emphasize again that this notion of interpretability is very different from what I think many other people in computer science call as interpretability. But the sense in which I use the term here is entirely in analogy with traditional numerical methods. Okay, so the work is still ongoing, because, as I said, we are still learning a lot about this, and I think there is a lot more, I think, that remains to be explored. We are actually looking for good students to carry this forward. So until this point, it is basically a two-man army. It's just me and Prabhu working, but we are looking for students to take this forward. And there are many exciting and interesting things that to look into. So we are doing, for instance, some theoretical analysis of these kind of networks to get precise convergence rates. Handling boundary conditions is slightly non-trivial because in some sense, these are generalizations which inherit the same drawbacks as traditional meshless methods, one of which is handling boundary conditions. So handling boundary conditions requires a little bit of care. And at least as far as I'm concerned, there are some very exciting things to be explored in the context of 3D simulations in solid and fluid mechanics. And there are very important problems, and framing it as in these models in the network language allows you to easily parallelize them and deploy them on large-scale GPUs. Okay, unlike, so you don't need any additional any special overhead. So you have a lot of very good frameworks already for programming deep neural networks. You can use any one of those to implement our methods. Okay? And of course, differentiable programming is all the rage, and it fits naturally with the kind of things that we do. So those are also things that we are looking at. Now, to close up, the larger question still remains, right? So can we interpret general deep neural networks? I don't know. Okay, I think that's a much more difficult question, and I see our work as a first step towards that. There's a lot more to explore, but there is one interesting insight that kind of comes out from this work, which is that if you have a deep neural network of whatever architecture, be a convolutional network or whatever it is, as long as the final layer is a linear layer, okay, you can represent it. You can essentially represent it as a linear combination of some global basis functions. So what you're essentially doing by minimizing a physics-based loss with such global basis functions is doing what is traditionally called as a Ritz approximation. Okay, in traditional Ritz approximation, you choose the global basis functions, and you find the coefficients that are needed to solve to fit that particular problem. Here, in some sense, deep neural nets learn both the global basis and the corresponding coefficients. So this gives you some handle, at least this way of looking at things tells you that there is some rationale for choosing the number of neurons in the final layer alone. For instance, if you think that you need some, let's say, 10 global basis functions for some reason to capture the solution, the final layer of the neural network should have 10 neurons, but it doesn't tell you anything about the intermediate hidden layers, the other hidden layers, or other than the fact that they serve to inform the complexity of the particular basis function, the global basis function. And again, this interpretation is not that great because it really doesn't help you with finer questions like, okay, I have a solution which obviously does not work in this region. What do I do? How do I locally refine that? Okay, there's no way to extract such local information from this kind of models. So I think that the larger problem of interpretation is still open. But the way I see it is that the kind of models that we are sparse architectures that we are proposing is a first step, and hopefully with these kind of hybrid models which stand between traditional methods and deep neural networks, we can gain some insight and draw upon the best of both worlds, and hopefully go towards interpreting these kinds of really massive models. Okay. Good. So our work was recently published in the Journal of Computational Physics, so you're welcome to check it out. So, and our code is completely open source. So here is the Git repository for the code. And this is something which is really neat because, and all credits to this go to Prabhu. Prabhu has this beautiful automation package called Automan, which thanks to which every single result in our paper is reproducible. Okay. So you can, it's not just that our code is open source, but every single run is reproducible. So you know exactly what parameters go into it. So you can verify that every single result that I show is actually true. And this, all credit to this goes to Prabhu. He has done an incredible amount of work in creating this beautiful automation framework, and we've just adapted that to our particular work. So please feel free to check it out. I think that's pretty much what I have. Thank you very much for your time, and if you have any questions, I'll be glad to answer them.
Thanks very much, Ramachandran. This is a lovely talk. I cannot say I understood everything, but that's my limitation. But I could know that it was a very lovely piece of work and very nice talk.
Thank you.
So anyone, if you have questions, just feel free to unmute and ask the question.
Hello, Amudan, can you hear me?
Yes. Yes, Harish. Hi.
Yeah, hi. Great talk, Amudan. So I have one question, right? So the main advantage of, let's say, using deep networks for solving PDEs is in higher dimensions. Is that right? Because in lower dimensions, you said that simple finite elements and meshless methods work well.
So that is a question for which I don't have a concrete answer. What I can tell you for sure is that in lower dimensions, there is no incentive to use deep neural networks. Whether deep neural networks are useful in higher dimensions, that is something that is thrown around a lot in many of the papers, but there are very few papers which actually show concrete examples that justify it. Now, the standard argument is something like this, right? So if you look at, let's say, a Monte Carlo sampling of a given, for computing an integral versus a quadrature-based algorithm to compute an integral, the quadrature-based method quickly runs into the curse of dimensionality, because as you increase the dimension, the number of grid points needed to represent the integral, to compute the integral, grows exponentially. Whereas if you have a Monte Carlo algorithm, then that in some sense breaks the curse of dimensionality, because it just traces the probability distribution. Right? So in that sense, it's good. Now, what can be shown is that theoretically, if you take a Monte Carlo sampling, that is structurally similar to a deep neural network. A given if you have a Monte Carlo sample with a certain number of draws, that can be shown to correspond to a deep neural network of a particular architecture. Okay, and that is the best argument I've seen to state that if you look at a higher dimensional problem, the deep neural networks break the curse of dimensionality. But what happens is that typically many of these statements are made in the context of function approximation. Okay, and that is quite different from solving a partial differential equation, because the losses are different. Okay, and the introduction of derivatives makes a non-trivial difference. So it's not clear to me if the curse of dimensionality will be overcome by deep neural nets in higher dimensions for these class of problems. And physically speaking, right? So if you look at most physically relevant partial differential equations, they are in 1, 2, or 3 dimensions. Of course, there are exceptions. In quantum mechanics, for instance, the Schrodinger equation is in a very high dimensional space. And people have been applying deep nets to solve the eigenvalues there, for instance. Now, so I don't know the answer to that question, but certainly in lower dimensions, there is it's not as efficient as traditional methods. We are actually doing a bunch of simulations right now and some analysis to get to the root of precisely this question. Okay, because this has been bothering us for a while now, and we still don't have a handle on this. And if you have some insights, I would love to learn from you.
No, I mean, but if this field is getting hard, it means that there must be some kind of a benchmark problem which deep networks succeed, but classic methods fail, right? There must be some benchmark problem.
So surprisingly, if you look at many of these problems, they typically solve lower dimensional problems and show that it works. And when it comes to higher dimensional PDEs, there are papers for sure. There are some benchmarks, but I don't think they compare it with traditional methods, because I've seen papers with 8-dimensional Laplacian equation. Sure, I mean you would really die if you use a classical method, because you cannot even store the mesh in the first place. But they get some good results with deep neural networks. So I think but there are no standard benchmarks. That's true. But we are looking into this. We are it's in a pipeline to look precisely what role dimensionality has to play in high dimensions. Yeah, that's something that we're looking into.
Yeah, thank you. Very interesting. Thanks.
Yeah. So I see a question on the chat by Sanjay Bhatt. Shall I take that first?
Yes, please.
Yeah. So the question reads, in what way do we expect neural networks to improve over finite elements? In other words, if FEM methods work well, why look for NNs? That's a fantastic question. So honestly, don't look for NNs. It's a waste of time. It's for lower dimensional PDEs, because the mathematical theory of finite elements is far richer than the mathematical theory of neural networks. And this is because, of course, finite elements has been around for a very long time. And probably, I think if we wait for a few decades, the neural network theory will also become that, that rich. Okay? That's but at the current status, right, in scientific machine learning, the use of neural networks is kind of ad hoc. And I think that is something that there are lots of interesting results. For instance, one set of results which I really like recently is that ReLU deep neural networks there exists a ReLU deep neural network that gets the same accuracy as any traditional numerical method like finite elements or certain class of meshless methods or HP refinements, etc., etc. So there are some interesting results in approximation theory in the context of ReLU deep neural networks, which are very interesting. Okay. So in that sense, theoretically, there's a lot of work to be done and there are exciting opportunities. But practically speaking, if you want to solve a differential equation, let's say in 2 dimensions, let's say you want to solve a complex elliptic partial differential equation, it's a no-brainer. Choose finite elements. It's really that simple. I think there might be one place where I think these methods could be helpful is differentiable programming. So if you, for instance, want to solve an inverse problem where each of the forward runs are very costly, and you can instead replace this particular complex finite element formalism with a deep neural network. In that case, definitely there are definite advantages in using a deep neural network based method in comparison to finite elements. Yeah, that's definitely there.
We have 2 raised hands. Please, just unmute and ask.
Yeah.
Yes.
Hi, Amazon. This is Shyam from Mechanical.
Hi, Shyam.
Hi. A very nice talk. Really enjoyed the presentation.
Thanks.
So I just wanted to ask, in general, a lot of these physics-based PDEs, we are also worried about at some sort of adaptability or increasing the number of mesh points and things like that.
Mm-hmm.
So how does your model address such an issue when you want a better representation through a larger number of points when some features are, or the gradients are changing more rapidly and things like that?
Exactly. Yeah. That's a great question. So the nice thing about our method is that if you once you compute the solution, right? So you know exactly where the nodes are located, right? So if you know that the solution is not good at a particular point, you can throw in more nodes at that point. And throwing in more nodes is exactly the same as changing the architecture. But now you have a very precise handle on how to change the architecture. You can say that, okay, I place a node at this location, which corresponds to having an additional neuron in the network with a specific weight and a specific bias. Okay, so in that sense, you are able to automatically get a first approximation of where it should go to, and then you run the optimization algorithm and to work out the precise details.
Right. Yeah. So
Yeah,
I
so in
was
that
just
sense,
thinking
yeah.
that that essentially can be quite helpful, especially when you have multi-material interfaces.
Yeah, absolutely.
And when
Yes.
the features are evolving, I think that can come really handy.
Yes, that's the idea. So the idea is to have a method which kind of sits between the two things, right? So it should have some features which are traditionally considered advantages as scientific computing. So if you have some handle on how to tune the parameter, how to tune the model to make it better, like what we have in finite elements or meshless methods, if we can port those advantages to these kind of sparse networks, then we can have the best of both worlds. So that's one of the things that which we can do relatively easily with our methods. Yes.
Yeah. Fantastic. Okay. Thank you.
Yeah.
Hi, this is Bharat from Earth Sciences. So
hello, Bharat.
Hi. So physics informed neural networks of PINs have been receiving a lot of attention in our field, particularly for wave propagation and wave simulation.
Yes.
The problem that we have is that the coefficients vary with space. So the coefficients of the PDE itself, which is the hyperbolic wave equation, vary with space, and it is not clear how well pins can handle coefficients that are variable over space. And as you mentioned, they are being used because we would like to solve the inverse problem to retrieve the coefficients.
Exactly.
So we have to do the forward solves a number of times. So
Yeah.
I would like to know your insights and your comments on this.
Yes. Actually, that's a great question because especially when it comes to hyperbolic PDEs, PINs have a lot of problems. So even a simple, I think there was recently a paper from I think the Berkeley group, where they showed how PINs can be notoriously bad at capturing these wave profiles. Okay, especially if you and they come up with a lot of interesting solutions for that. But in our method, it's relatively easy to handle because what you're essentially saying is that if you have one of these hybrid finite difference and what do you say, spin kind of approaches, then at each time step, the nodes have to adapt locally to where the wave profile is. And that is kind of naturally present in our model. So we can handle that in some sense more naturally. In PINs, it is slightly more involved because of the fact that you either have to splice your entire simulation into time slabs. For instance, instead of solving it as a full space-time solution, you solve it in each time slab. And then you keep marching in time. Or you can consider the full space-time, but that really doesn't work in higher dimensions. Even in 2 or 3 dimensions, it can be very costly. Yeah.
Thank you.
Hello.
Yeah.
Sir, we have a question regarding the time stepping of mergers. So in the traditional merger solution, we'll have be restricted to the CFL thing. So is it the same thing in
Sorry, Gaurav, I'm not able to hear you very clearly. Could you? I'm not sure if the problem is at my end. Okay, I have full.
Can you hear me? No?
I can hear you, but your
I will
voice is
type it.
kind of. Yeah, if you could type the question, that would be great. Thank you.
So I think
Yeah,
I got the question. Let me just interpose and just explain the question, then you can answer. His question is, are we restricted for the Burger's equation with the time step constraints that the CFL time step constraint is the question.
Yes and no, for the simple reason that the spatial discretization is handled with automatic differentiation. Okay? So if you go back to the Burger's equation here. Okay, not here. I will show a different equation. Yeah, if you look at this equation, it's, are you able to see this equation? UN plus 1 equals, yeah. So if you look at the same discretization, a similar kind of discretization applies for the Burger's equation. But the crucial point to note here is that the spatial derivatives are not computed using finite differences, but they're computed exactly using automatic differentiation. So you do not have a typical constraint like a CFL condition that you will have in the solution of Burger's equations in standard scientific computing. So like finite volumes or finite difference methods. But what you will have is a stability constraint because of the size of the time step, because it's still time stepping. Okay, so how irrespective of how you calculate this, there is a dependency of the solution, a stability of the solution on the time step. Okay, so in that sense, you have a time step requirement, time step constraint, but there is no CFL-like condition that couples a space discretization and time discretization, because these are handled automatically with automatic differentiation.
And just wanted to point out, so this is also an implicit time.
Yes.
So
yeah, it's implicit because you see that the derivative is at time step n+1, and your solution is also at time step n+1. Yes.
So it will be accurate if you go faster, if you take a bigger time steps and all.
It really depends. I mean, so if you're close to the shock front, or at least close to the time when the shock is forming, then large time step won't help. Okay, because there you will have inherent limitations because of the stability problem, right? So this dependency on time here that you see in the implicit scheme, that will show up. So that will flare up and that will cause some problems. But if you look at the space-time solution, on the other hand, that doesn't have those constraints because you're treating both space and time on an equal footing, and you don't have the equivalent of a CFL constraint. But what will happen is that the nodes on the edge on the shock front automatically get a finer resolution, right? So the widths of the nodes get smaller and smaller. So what you would expect as a time step requirements translates into an adaptive refinement of the zones of influence, and that's something that we see automatically. So in the space-time version of Burger's equation, you really don't have the kind of constraints that you have in traditional solvers, but in the implicit finite difference and spin models, you will have a stability constraint based on the time step alone, nothing related to the spatial resolution.
Yeah, thank you.
Yeah.
So Amuthan, this is Anirudh. Follow up. So thank you for the very nice talk. So following up on that, so which one would you prefer? Would you prefer the space-time solution or the implicit finite difference?
Yeah. So at least for all the simulations that we have run, the implicit finite difference seems to outperform space-time solution. For instance, in the Burger's equation, if you look at the solutions computed by the implicit finite difference scheme and the Burger's equation and space-time scheme, you see that there are these additional oscillations and dispersion around the wavefront, shock front. It's not precisely captured. So this is directly related to how we are how the nodes adapt themselves. So it's either a problem with the number of nodes that we have. We need to solve a larger model, or it is probably having to do with the fact that our nodes are isotropic. Okay? So we have methods. We have some ideas which we are testing out, which will alleviate some of these problems. It's still work in progress, so I don't have a definitive answer. But what we know for sure is that the implicit finite difference scheme that works really well. So at each time step, you solve a neural network model, and you keep matching in time. So that really works well, and it captures the solution, and it's much easier to control also.
Right, but as you told in that answer to Gaurav that it will then have that CFL-like constraint on the time step, right? Which you will not have in the space-time method.
Absolutely, absolutely. Yeah, there are pros and cons. So what happens is that if you use it as a space-time method, the number of nodes that you require also increases. So roughly, it's like saying that if I have a 2D problem, which depends on two spatial dimension and one time dimension, solving it as a space-time means that you're solving a 3D problem. So the number of nodes that you will need to capture the solution is much larger.
But you're getting the answer all together, right? You're getting the answer for all time at once.
For all the time steps in a given window, right? So if I want to move further, then I'll have to resolve the entire system on a larger domain. If, for instance, if I compute it for a time interval of, say, 0 to capital T, and I want to understand what happens from capital T to capital 2 times capital T, I'll have to essentially solve another problem. Whereas with these kinds of implicit finite difference schemes, you really have to just march forward and get the solution. And the number of nodes are also much smaller. This probably is a consequence of using a smaller number of nodes, and also the fact that we're using isotropic nodes. I think with a little bit of work, we can overcome this. We are still working on that. We don't have a solution yet, but hopefully sometime soon in the future. Yeah.
So also you're interpolating in time here, right? In the space-time, because you do not have the solution at a particular time. So
yes,
aren't you interpolating in time? Your post-processing.
Yes, I mean, in some sense, what you have is, if you look at the nodes, right? And so here, yeah, if you look at these, right? So these are the initial placement of the nodes. And what we have shown is where the nodes are located at various snapshots. Now, if you want to understand the solution between this time and this time, of course, you would want to interpolate the solution. But this is something which is common to any kind of a finite difference scheme. If you have a finite difference time stepping, you will automatically need to interpolate between time steps if you want to understand what happens in between. Yeah.
Okay. Thanks.
Yeah, I should also point out that there is the space-time solution cannot be interpreted as a time stepping scheme, because you can clearly see that they are not really placed as nodes, and they don't cluster as in time slices. They're located everywhere in space-time, which means that it's a fully asynchronous integration. It's not like a regular finite difference.
Any other questions?
Yeah, hi.
Oh yeah, Yes. Hi there, Amrit. Yes.
Hi. Yeah. Hi. So I had a question. So in traditional methods, the nodes are fixed, right?
Yes. I mean, it depends. I mean, if you there are variants, all kinds of variants. You can have fixed nodes in finite elements. You can typically have fixed nodes, but in meshless methods, you can allow the nodes also to move.
But that is something that we guide, or they are guided by the equations like we are seeing in SPINN.
So in the context of SPINN models, right, both the location of the nodes, the zone of radius of the zone of influence of the nodes, and the weights associated with the nodes are trainable parameters. They are all outputs of the model, the training of the model.
Okay, so do you think they have a physical meaning? So like, because that will help in like determining the initial number of nodes, because that is fixed throughout the simulations, right?
Yeah, absolutely. So the physical meaning is kind of what I've been talking about, right? So this represents, if you look at the traditional meshless approximation, it tells you that here is a particle which is located at this point, which has a set of properties, and a linear combination of these properties is what gives you the final solution. Okay, the precise way to enforce the connection is using what techniques like what people use in smooth particle hydrodynamics, where you first write out the solution in kernel form, and then you systematically approximate the kernel in terms of particles, and you represent the solution as a collection of particles having certain properties. And once you have that kind of an interpretation, that can be translated almost entirely to what we have in SPINN. Yeah, that can be done.
Okay, so is there a systematic way to determine, like, given a problem, that okay, this should be the number of nodes?
You can have
like
ballpark estimates, okay? Because ultimately these are numerical solutions. So what, depending on the level of refinement, you will have more and more accurate solutions. So you can start with an initial ballpark estimate, and of course, depending on the solution, you can always refine the solution as required.
Okay, thank you.
Yeah. So I see one more question on the chat. Should I take that?
Yeah, please.
Yeah, okay. So have you tried SPINN on nonlinear wave propagation problems like the hyperelastic material with Monte models? How effective? Okay, so we haven't tried nonlinear wave propagation, but we tried the Burger's equation, right? So it's not a wave propagation problem, but you can see that there is a profile which is moving non-linearly, and it's kind of sharpening out, right? So in that sense, yes, but not in general. Okay, we have not tried this hyperelastic material with Monte constitutive model. We haven't tried that, but we have a long list of models in the pipeline to test. And yeah, wave propagation is something that I'm interested in. That was the topic of my PhD work also, Monte models too. So definitely plan to visit that at some point. Okay, and yeah, inverse problems, yes, those are also all in the pipeline. We have not done inverse problems yet. We wanted to test out the as a first swipe, right, to the proof of concept where you're able to solve all the regular Devils and partial differential equations, right? So elliptic, parabolic, hyperbolic, linear, nonlinear, etc. So we have a good degree of confidence that it works. And the next step is to really, increase the level of complexity in tackling partial differential.
So I guess we have kind of really asked lots of questions. Maybe we should give Amuthan a break now. And maybe if you have other questions, you can contact him. He's our own faculty. Yes.
Yeah, please feel free to reach out anytime.
Yeah. But it's great to have so many, so much interest from people from across the departments, because I feel that kind of gives some meaning to the existence of the center. I mean, this is the main goal that we want to achieve. And I'm going to use this platform to encourage other CMInDS faculty to give talks, so that we can have such a sort of collaboration across different faculty. And thanks, Amuthan, for kind of giving us an example to follow. In that, I just really found it very exciting that there
I
were
should,
so much interest and excitement from people across different departments.
Yeah, I
And
should definitely thank you too. Yeah, because I think this is a great forum for me to interact with people that I would otherwise not interact. And
yes,
this
yeah.
interdisciplinarity that is fostered, that this center fosters is really great because it allows me to discuss ideas outside my small cocoon, and
Yes.
that's all
Yeah,
good because
yeah,
it helps me grow. And so thanks.
In my mind,
Thank you.
this is the main reason for the existence of the center, and you have
Exactly.
made it worthwhile today. So yeah.
Thank you very
So
much,
great.
yeah.
Thanks a lot for this exciting talk. And if you have other questions, please write to Amuthan. And better still, maybe we will have some collaborative projects coming up after
Yes.
this talk. And also, I
Okay.
expect self-volunteers for giving talks in CMInDS seminar. So please write to me if you would like to give a talk on AIML related topics. And so with that, we will conclude today's talk. Let's give a virtual applause to Amuthan, and thanks very much.
Yeah. Okay. Thank you very much.
Yeah. Okay.
Yeah.
Bye. Yeah.
Bye. Bye, everyone. Yeah.